Oh, okay, so for the first one, it was just a hydrostatics equation, and just had to convert everything to the right units, and it works out. It can increase or decrease because it could be going up or down, and it drops due to the viscous forces because it's viscous. It's going to be resisting the flow. This is from Bernoulli. Because the velocity is decreasing, the pressure must increase to compensate. Here, mistake I made was I just used 1,000 for the density. I just used the density from 160 degrees, and then the delta density from rho gh will get you the delta p. For this one, first I calculated the volumetric flow rate for each nozzle because there's two of them. Then I got the velocity from the area. And then I got the tangential velocity because it's coming out at an angle, and that's basically the water leaving the nozzle. And then I got the angular velocity from omega, the omega equation, so 2 pi n dot, which is the RPM we were given that. I had to convert that, and you get the omega, and then from there I got the angular velocity. And because they're going in opposite directions, I subtracted them, and based on the way that I defined my positive direction, I got a positive velocity, and it could be negative if I switched it. Okay, so here first I got the molecular weights, and then I got the basically the the weight that each balloon had to carry because there's 42 of them, and then I got the density of helium from here, which is that, and then basically two volume equations. I set them equal to each other. It's just the volume of a sphere, and solve for the density. And here it's just the mass that each balloon is carrying over the difference in density, and then set those equal to each other, and then solve for the diameter. And I end up getting 5.2 feet per balloon. So for so for this one, I start with the full Bernoulli, no friction loss. That's at the same height. From continuity, I got that the velocities are the same, so I canceled all that stuff out. For the non-flow work, I substituted in that, solved for W dot, and then just plugged in values, and do unit conversions. And I end up getting this because it's only at 72% efficiency and it's a pump. We're gonna have to supply more work. Here, I didn't put kinetic energy, and then you would lose friction loss is a poor assumption here because if the pipe is super long, there's more basically pipe to lose friction energy. And then for the last one, start with the full Bernoulli and continuity, cancel out height here because I have that as 0, no work, no friction loss. Here's the simplified. Then you can plug in from the continuity the velocity as in terms of volumetric flow rate and area. And then negative height because it's down here. Then here you just plug in everything and do your conversion on the volumetric flow rate. And I got 1,065. I think I ended up getting the same answer here, or I must have had like a and then for the force, I didn't account for the pressure force. And then I canceled out that because gauge pressure is 0. Oh, and I canceled out, because it's only exposed atmosphere, and we're able to work in gauge pressure, which means that P2 is 0. And here, rearrange this all for the force and the bolts, and then plug in the known values that we have, or use the continuity to plug in for values that we have. And then I end up getting that for force. Thank you.